Hello everyone and welcome to fifth lecture of this course, Digital Elevation Models and its Applications. And today's topic we are going to discuss about the importance of spatial resolution with DEMs. Because a spatial resolution of any DEM will decide indirectly the quality of a DEM. There are some other things which we will also discuss which finally constrain the quality of a DEM. So, first what is spatial resolution? Those who have gone through the courses on GIS and remote sensing might be knowing what is a spatial resolution, but those who haven't, just for refreshing their memories, that in remote sensing resolution means the resolving power, and here that basically means capacity to identify the presence of two objects which are very closely spaced, and capability to identify the properties of two objects. How, what if it is remote sensing data, then what is their reflection or emission and so on and so forth. But in digital elevation model, basically when we say it's a high resolution or finer resolution digital elevation model, that means we can see much more details of the terrain in a digital elevation model. So, higher the spatial resolution of a digital elevation model, better details we see, and in contrary to this, if a spatial resolution of a DEM is coarser, then those much of details we will not be seeing. But this is a relative term. When we say higher or finer resolution, but today say 30 meter may be a higher resolution, but tomorrow maybe 15 meter, 10 meter or even 2 meters may be higher. So, things keep changing, and especially when we are using digital elevation model along with the satellite data, then sometimes we try to match the spatial resolution of satellite data as well as digital elevation model. But this is not necessarily, but it becomes convenient to address many issues related with the spatial resolution. But most important thing in digital elevation model, that we talk about two types of resolutions. One is basically horizontal resolution, which we refer as a spatial resolution, and which is the spatial frequency at which samples are taken or modeled. And though when digital elevation models are constructed, as we have seen using different techniques, the spatial resolution will depend on the input data. If these are being constructed through remote sensing data, then the spatial resolution of remote sensing data will control the spatial resolution of a DEM. But if digital elevation models are being constructed using interpolation techniques, then at that stage we can decide what should be the spatial resolution of a target DEM. But this horizontal resolution is basically the XY directions in which the data is being generated or recorded for horizontal resolution, that is basically spatial resolution. And as we know that this is always square in shape. Whereas there is another resolution in case of digital elevation model, which is a vertical resolution. And that vertical resolution basically that how frequently DEM can record a difference in elevation, or in other words you can say a least count, and this may be an integer value or maybe values in feet. Generally the elevation values are represented in meters and maybe even in decimal. So, you may have even real numbers for vertical values. Now, it is generally it is seen or experienced that the both resolutions are not same, and therefore, the jet factor, which plays a very important role while driving various parameters using digital elevation models, for example, slope and aspect and other parameters, at that stage we have to see that the jet factor equates the horizontal resolution with vertical resolution. So it is always good to understand before we imply a particular digital elevation model these two resolutions. What is the spatial resolution, that is the horizontal resolution of a digital elevation model, and what is the vertical resolution, that is basically the least count. So generally it is in meters, but you may have even in centimeters or in decimal and so on and so forth. Generally very relatively coarser resolutions will have in meters, least count may be 1 meter, but finer resolutions may have in centimeters. So the least count is relatively a very small value. These are two important resolutions related with digital elevation model, and one has to remember these resolutions, use very carefully when we drive various products using digital elevation models. Vertical resolution is generally higher as compared to, or finer as compared to horizontal resolution. You may have a least count of 1 meter for vertical resolution, but you will be maybe having 30 meter spatial resolution. So that is what it is meaning here. Now as mentioned in the beginning, that alone digital spatial resolution alone does not determine the accuracy of a digital elevation model or a quality of a digital elevation model. There are various other factors. So before we go for other factors, two terms which I would like to discuss here, generally many people use them interchangeably or synonymously, which is incorrect. So the first term in this in our parlance or digital elevation model domain is the accuracy. And as you know that accuracy is a statistical concept which states the likelihood or probability that a particular set of measurements are within certain range of true values. So what is the, we generally say what is the accuracy, but then another terms comes, is a precision, and precision is a statement of smallest unit of measurement to which data can be recorded. So as said in GIS that you know that the accuracy we have to maintain or keep at this errors, we have to keep at the minimum, because error propagates in GIS while doing the processing. Same thing we can say in case of digital elevation model, that while doing any or driving any derivatives, we should not bring some new errors, or that means we should not lose the accuracy. But the precision cannot be changed once the data has been generated. For example, precision in case of satellite images, we can say the spatial resolution. So that is the smallest unit of measurement. So if it has been recorded at 10 meter spatial resolution, then by no means basically we can change or improve the spatial resolution of a data set. So the precision cannot be changed, whereas the accuracy, that means in other words, the errors can be kept at minimum so that we maintain a high accuracy. These two terms have to be used very carefully. However, as said that sometimes people use them interchangeably. So finer resolution DM or higher resolution DMs may offer great precision or greater precision, although not necessarily greater accuracy. So they have been recorded at a using a very high vertical or spatial resolution. That means they might be having a better precision, but accuracy wise, that means at the time what was the error in the data sets, how the processing has been done, that will be controlled. So overall the accuracy or quality of a digital elevation model also depend on these two parameters, that is accuracy and precision. Now for example, you may have a sensor with a 10 meter spatial resolution, but suffers from systematic errors, noise or random errors, which may be less accurate than 1 kilometer grid, and it is more precise but less accurate. So this keep happening. So once the data is with us for further processing, for to drive various products out of a digital elevation model. All these things should be assessed. There is a one term which we use is metadata, that is the information about the data, or also we call data about data. So once, if you have downloaded a digital elevation model, maybe a free digital elevation model, say SRTM or global DEM, then one must look through the metadata, and metadata will give you lot of information, including the information about spatial horizontal resolution and vertical resolution, and also it will give you about the accuracy and precision. So these values will help us while using such products and making and using them to drive some other byproducts from them. Now just comparing different spatial resolutions, what we can see here that when we represent this area is having 71 square meter and there is a polygon. So two different types of units are here, but when we overlay a grid of 16 by 16 cells, and this cell the cell size of this grid is 1 meter, the overall area which we are getting is 73 square meter of the only of this shaded part or this yellow colored, and what we are actual polygon area is 71 square meter, but at this resolution we are getting higher area for the same polygon because of coarser spatial resolution. But when we go for further coarser resolution, we may reduce. In this particular case, it has reduced to 72 square meter. This is a 2 meter cell, 8 by 8 cells grid is there. Whereas if we go for 4 by 4 cell, that means more coarser resolution, 4 meter cell, 4 meter spatial resolution, and what we are seeing, we are getting 80 square meter area, because lot of area of this polygon is not falling, but when we are creating a raster of this one, then we may get a higher area. So the spatial resolution can create wrong areas for different polygons or different areas within a data set. So what we can mention in nutshell, that the smaller cell size can bring more close results generally, that is or versus larger cell size, higher resolution versus lower resolutions, higher features, that is the spatial accuracy, and lower features, that is also spatial accuracy, lower display, faster display. If it is a coarser resolution, it will bring faster display, slower processing in case of high resolution. In case of lower resolution, coarse resolution, it would be a faster processing, larger file size because of high spatial resolution. In case of coarser spatial resolution, you would have a smaller file size. But generally, only at the time of interpolation we can control spatial resolution. But spatial resolution, if the digital elevation model have come through remote sensing data, then probably we cannot at that stage control the spatial resolution. We have to depend on the spatial resolution of the satellite data itself. One more example of how different spatial resolutions will bring the terrain or the area completely differently. So if we take the rightmost image first, what we see, say spatial resolution is 110 kilometer. So each cell is representing 110 by 110 kilometer area. For climate models, sometimes we may use this because 110 may become roughly a 1 degree cell, and then if we go for 30 kilometer by 30 kilometer cells, then here what we are seeing that a lot of other different effects of climate change or models can be seen much better than relatively coarser resolution. But when we compare this precipitation pattern at very high resolution, then this is how it looks. So the original one is driving from satellite images. Now it is a lowered resolution at 30 kilometer by 30 kilometer, and then here it is much more simulated. Here is 110 by 110 kilometer. Why we play with digital with spatial resolution? Because sometimes we have to generalize the data or reduce the data so that it fits with our other data sets. Because when you are handling such data, say on a GIS platform, one data set may be having 10 meter resolution, one data set if it is having 10 kilometer resolution, then it is not good for any kind of analysis. So we try to bring sometimes a resolution close to that, and then probably we may deteriorate as per our requirements, modeling requirements, or the spatial model which we are using, that may require that the grid size should not be more than this and each cell should be of this size. So sometimes we try to deteriorate the spatial resolution of a DM or any other data set, and at that time one has to really remember that what kind of losses you will bring or what kind of errors you will bring into the data, the accuracy part basically. One more example is here, that if this character R has to be represented, this is represented by in this space in this case say 100 columns and 100 rows, whereas if we see one row by and one column, that means single pixel or single cell, we don't see anything about this character. But when we move 2 by 2, then we start seeing something, but obviously no sense can be made out of this. 5 by 5 is still not possible. When 10 by 10, some character is appearing, but it is confusing whether it's A or R. But as soon as we go for higher than 10 by 10, say in this example 20 by 20, then the shape of R starts appearing. But still there is a doubt whether it's A or R. But once we go for much more higher resolution, then we get a clear picture about R, and when 100 by 100, then it becomes further sharper. What does it mean? Basically that for every type of phenomena, there has to be up to a certain resolution. If we go low resolution or for objects, we may get the outline, but still there might be a confusion. So we need to have a optimum resolution for a certain type of processing where every object becomes very clear. So in case this is more common in case of satellite images, but still in case of a digital elevation model, these things have to be taken care. One more example of different spatial resolutions derived from different sources and of the same area. So on the right side, what we are seeing a 10 meter digital elevation model of national elevation data of USA, and this is big Cottonwood Canyon sample area. And as you can see that it is relatively coarser resolution, and therefore that much details about the terrain are not visible. If we compare this with 2 meter spatial resolution of the same area, but derived from LIDAR technique, and which has produced a very high spatial resolution digital elevation, and much more details about the terrain can be seen. In between, we are having a 5 meter spatial resolution DM, which is giving much more details as compared to 10 meter resolution, but definitely it is giving less details as compared to 2 meter resolution. Now it is not always possible to go for higher and higher spatial resolution. There has to be some limit, and generally when we are covering a large area, and one more discussion will come in this lecture about the scale. So when we are going for a small scale, that means going to cover a large area, then generally we do not go for very high spatial resolution and digital elevation model. But when we are covering a very small area, that means on larger scale, then definitely at that stage we require a very high spatial resolution DM. So different spatial resolution DMs can serve for different applications. That one has to, because for a very large area, if we go for very high spatial resolution, it would be too much data handling, and our results may not, or the target or model may not require that kind of details about the terrain or elevation. So it would be a redundant process if we go for very high resolution digital elevation model. There are some other examples derived of digital elevation models derived from different sources. The first two on the left side are DM ALOS, and this is prism 5 meter resolution of the same area at 30 meter resolution, but this is GDM, Ester GDM, global DM, and then SRTM 30 meter again. So when we compare this 30 meter, though it is resolution wise same, but the techniques are completely different. As you know that Ester GDM have been, or this DM for global DM has been derived using stereo pair data from optical remote sensing data, and for a hilly terrain we are seeing quite nice or sharp digital elevation model. Same time also with the SRTM, which is based on INSAR or radar remote sensing technique, is also giving equally good digital elevation model. But if we go for ALOS prism 5 meter spatial resolution, since the resolution, spatial resolution has improved significantly, and therefore we are seeing much more details about the terrain of a hilly terrain. So this is important, but as per the requirements, we should opt for different spatial resolutions. One more example is here that we are comparing of Banjara Hill, India at 90 meter resolution on top left. Then we are having a 30 meter resolution top right, and you can compare that huge difference between 90 meter, 30 meter. It's a 3D perspective view. Then C is the DM, which has been derived using Survey of India topo sheets of 50,000 scale. At this stage you can control the spatial resolution. So this must have been kept at around 60 meter or 90 meter exact, and then 5,000 scale topo sheets, because the scale is much improved. It's a larger scale topo sheets. You are getting much more detail, maybe even at same spatial resolution. So these bottom two are really bringing two different outputs based on two different scale topo sheets. So the at that stage the scale also, the input data scale also matters. This is what it is being reflected here. Now here in case of satellite images, we say as a pixel, but in case of digital elevation model or grid or raster or a grid, we say is a cell. So it's the same thing here in that sense, that here we are saying pixel, but if I take this example for a digital elevation model, then it becomes cell size. The example here, this is illustrate that if I am having a situation something like this, that in between there is a house and rest of the area is a blank, but at 30 meter resolution I am getting a completely a blue area. I am not getting any detail about this red area. But at 5 meter resolutions, when I go for a grid like this, at 5 meter grid, then I am getting an area about 1/4 area is getting this red and 3/4 is getting blue. And whereas if I go for 1 meter resolution, relatively compared to 30 meter, it is much more high resolution. So now I see the blue areas and red areas very clearly. Similarly here also, that different scenarios have been presented here, and this is a digital elevation model of a Kalstau basin at different resolutions, and what we see the details, what we require. So basically, if you are having a very high spatial resolution digital elevation model, you can deteriorate the spatial resolution. You can still make the coarser spatial resolution by doing the resampling of the data set, so that it fits with other data sets or becomes a suitable for a model. maybe a climate change model or some other models. But if I am having the data at a relatively a very coarse resolution, say 10-meter resolution, say 10 kilometer resolution, and if I want to improve the resolution, then it is not possible. So one way, that means the deterioration going from finer spatial resolution to coarser resolution is possible, but going for coarser to finer, though in computer you can always do it, but it will not improve the quality of a digital elevation model. That means it will not bring the details of terrain in even a resolution has improved, but original input was at a coarser resolution. So generally this is a one-way process, and this is what exactly it has been shown, that 20 meter, 200 meter, 400 meter, 800 meter, 1600, 24 and 4000 meters. And this is how you start seeing the deterioration of the details once we go for relatively a coarser resolution. Now, what are the effects of different spatial resolutions of DM over topographic wetness index, which is one of the products which we will be discussing in subsequent lectures. So this is one product which we can drive using digital elevation models, and what happens if we use different spatial resolutions. So three examples are given at 0.5 meter, that means 500 centimeter, 1 meter and 3 meter. At 5 meter, what we are seeing that this topographic wetness index is appearing completely different than at 1 meter or at 3 meter. So 0.5 meter, 1 meter, 3 meter, 5 meter, 10 meter and 15 meter. And in every product this TWI is appearing completely differently. So definitely at very high resolution, relatively here 0.5 meter it appears very nicely, but if I compare with 0.5 to 15 meter, there is a huge difference between this data, and it has been compared with the probes which are located here as black dots, as one can see here. So the spatial resolution of a digital elevation model will affect almost all derivatives which we will be driving through a digital elevation model. All products, it will depend. But as per the requirements, if choice is there, then we have to choose an appropriate resolution of a digital elevation model so that we get the quite accurate products out of a digital elevation model. And in this process, we should not introduce any errors in our products. So that's the situation here with the different spatial resolution DMs over topographic. One of the examples is given here. If because we can also use digital elevation models along with the surface hydrologic modeling on a GIS platform and can drive drainage network. So one products which is topographic wetness index, as we have discussed, at different spatial resolution the results would be entirely different. But at the same time, if we go for driving a drainage network based on surface hydrologic modeling where input is a digital elevation model, again if that same exercise is done at different spatial resolution, this is what we see here. That actually in a topo sheet, say Survey of India topo sheet, at 50,000 scale drainage is visible like this. But when we drive a digital drainage network using a Cartoset DM of 10 meter resolution, this is what we are getting. Much more detailed drainage as compared to what is shown on a 50,000 topo sheet. But when we go for 20 meter spatial resolution Carto DM, now these details about the drainage have reduced. We go lower or a coarser spatial resolution and we start seeing less and less details of drainage. 90 meter, again this example is 50 meter, 40 meter, 30 meter. So at different, and this is again a 90 meter, but this is SRTM. So this is Ester DM at 30 meter. Now you can compare Carto DM 30 meter SRTM 30 meter, and these two can be compared very easily, and whereas the outputs are coming completely differently, though the processing may be the same. That means the surface hydrologic modeling has been applied on different DMs in a similar manner, but the output you get completely different. So higher spatial resolution DMs might bring more detailed drainage network as compared to relatively coarser spatial resolution DM as shown in these two examples of 90 meter resolution. But one thing one has to remember, well, when we drive drainage network using a particular digital elevation model in surface hydrologic modeling, we also constrained by a number of cells which will be incorporated to drive a drainage line. So if we choose a smaller threshold, we are bound to have more drainage than choosing a large value. For example, if I choose 100 cells, that means if an contributing area is 100 or more than 100, then there will be a drainage network which will be derived. So up to 100 cells, drainage network can be derived. But if I choose a threshold at 500, then coarser or less detailed drainage network will be derived. So while doing this comparison or comparative study, one has to keep this threshold at constant, then only you would be able to see these kind of results. But if we keep changing this threshold value, then we will not get the accurate results in that sense. So the drainage density also depends what the threshold we choose while doing this surface hydrologic modeling using a particular digital elevation model. So if one more topic which comes here is now that we will be seeing about the scale, because here once or twice we have already brought this discussion, say here topo sheet of 50,000 scale. But before we go for directly towards the scale, there is some comparison between different digital elevation models, and there most of these are free digital elevation models, their spatial resolutions, their accuracies, and which has been collected through metadata, and then their availability is also there. So first we go for SRTM, one of the very first free digital elevation models. Initially it was available at 90 meter, now it is also available at 30 meter, and the accuracy was about 6 to 8 meters. And when we say this accuracy here, this is, we are talking only about the horizontal accuracy. GDM, which is global DM aster derived from stereo data of 30 meter resolution, this varies because for hilly region it is different, for plain areas it is different. And the same is with the spot HRS, and though the ready-made digital elevation models are not available, but if we drive digital elevation models using say 20 meter, 30 meter resolution data, we can achieve of about 8 meter accuracy. Then word DM, a loss prism can provide a very high spatial resolution relatively so far, and a very high accuracy as well. Then GeoDEM to Iconos provides the data at 1 meter resolution. You can have resolution at 1 meter or 2 meter, and you will have accuracy of 1 meter, 2 meter, and so on. Most of these data are, many of such data are available on internet, which can be downloaded. Few are also getting added here in the list. Now, as we have discussed that the spatial resolution is the key characteristics of a DM, and different applications may require different spatial resolution DM, which we have also discussed. So depending on if one is working on a climate change model or in a hydrological model which is covering a very large area, then perhaps you may not require a very high spatial resolution DM. But if somebody is working in a very small area, then definitely one should go for as far as the highest available spatial resolution DM. Selection of appropriate resolution DM will ensure that that you get exactly what you want. but also one can save resources and ones don't want to over specify. That means that though area is very large, though you don't require a very high spatial resolution DM, but unnecessarily you are handling a high spatial resolution DM, and at later stage you might deteriorate the spatial resolution to fit with other data sets of the model, and therefore that is redundancy is present. And choosing an appropriate cell size is not always simple. And the choice becomes, this question may be raised that what a spatial resolution? Okay, I don't know anything about my area. I don't know much about what I am going to do with this. So what spatial resolution I should start? Because choices are becoming wide now, and therefore this question may become little larger. So the best thing is one has to see what are my targets. For what I am going to use digital elevation model, and accordingly one should go for that particular spatial resolution. And these are the factors which should be considered while spatial resolution of a DM can be decided. That it is well known that the grid cell size of a raster grid elevation model has significant effects on derived terrain variables. Because these variables will depend on what is the spatial resolution, and examples are given here like slope, aspect, plan or profile curvature, wetness index, drainagement network, and many parameters which we derive from a digital elevation model. So choosing an appropriate spatial resolution DM is very important. And that is for the input data and the application analysis that can be performed using such digital elevation, and the size of the resultant database compared to disk capacity, because we may be using a high spatial resolution, may not be required, and necessarily we may be occupying a large space on the hard disk. So that is the redundancy. If it is not required, one should not go for high spatial resolution unnecessarily. And also one should think the desired response time, processing time, and other issues as well. So spatial resolution versus scale now, and that spatial resolution refers to the dimensions of the cell size representing the area covered on the ground, which we know now, and therefore if the area covered by a cell, for example, by 5 by 5 meters, the spatial resolution we call as 5 meters. Higher spatial resolution of a raster, the smallest the cell size and thus greater details are there, but at the same time it will occupy a large space on hard disk, and same time it will require more processing time. So if you are handling a very large area at very high resolution, you know that what kind of problems one is going to face while doing the processing of such data set. And this is the opposite of scale. But before that there is a statement which is very important to understand here, is that as long as the data inside a computer on a hard disk, there is no scale. That means the digital data does not have any scale. The scale is frozen or fixed once it is displayed or printed on this one. So one has to remember that a scale is not directly dependent on a spatial resolution. So digital data do not have, for example, a satellite image. That image may be representing an area of 100 km by 100 km. Same may be given example for a digital elevation model. So that may be representing 100 km by 100 km area. So now that digital elevation model I can print on a A4 size, or I can print on A2 size or A3 size. So now when I print the same area on A3 size, I am improving basically I am printing on a larger scale, but the spatial resolution is frozen there. So the scale has changed when I have printed, but as long as when inside the system, then there is no scale, only the spatial resolution is controlling everything. So one has to remember that scale is fixed or frozen once the data is displayed or printed. But if it is as long as it is in the digital form inside a computer, then there is no scale, the spatial resolution is more important. And this is the major difference between while handling the digital data. So, smaller the scale, less detail it will show. For example, a DM displayed at 1:200 scale then shows more details, appears zoomed in than displayed on 1:24,000 scale. And similarly, if this DM has a cell size of 5 meters, then the resolution will remain same no matter what scale it is displayed. So, you may change the scale, but also as mentioned earlier that the resolution is not going to be changed when you display or print it. So, that is very important here. So, this brings to the end of this discussion about spatial resolution, vertical resolution, horizontal resolution of a digital elevation model, and two other parameters which we consider while assessing the quality of a digital elevation model, that is the precision and accuracy, and then resolution versus scale. And remember that finally that digital data do not have a scale till they are in the system. Once you print them or display them, then the scale is fixed or frozen. Thank you very much.